Next, we will create a raster using the curve number. As we can see in the article, this CN is an empirical parameter by the Soil Conservation Service used in hydrology for predicting direct runoff or infiltration from rainfall excess. It considers the characteristics of land use and soil type. The values of CN range from 100 for impermeable surfaces to 30 for very permeable soils with low runoff potential. The CN map was obtained using both the land use type data and soil type. CN values are published by the SCS for different land uses and soil types, as a high CN means high runoff and low infiltration, and a low CN means low runoff and high infiltration. High values of CN were assigned to a scale of 5, and low values were assigned a CN value of 1. So, as we saw at the beginning of this video, we already have the necessary base data. And as the next mentioned, we'll need to start by using the land use and soil type to assign the curve number values. Once we have that, we will reclassify the data according to table 2 from the article. As we saw in the text, the curve number is an empirical parameter developed by the Soil Conservation Service, so we'll start by visiting the SCS website. Just type Soil Conservation Service curve number and open that result, this one, from the Hydrologic Engineering Center. And if we scroll down, we can see some parameters. Under cover, we have the different types of land use, and on the right side, the so-called hydrologic soil groups, ranging from A to D. The values shown are the curve numbers, which are assigned based on the intersection between these two sources of information. One important thing to note is that, obviously, when you apply this type of methodology, the land use categories you have won't exactly match the names shown here. So you'll need to adapt or approximate your data to fit your specific context. If we take a closer look to this shapefile, the soil hydrologic groups, I'll just activate the layer for visualization. We can see that there are gaps in the data. So we need to correct this, because if we don't, we will be introducing errors into our calculations. There are several ways to do this, but what we are going to do here is go to the geoprocessing tool and search for symmetrical difference. For the input features, we are going to drag and drop the soil hydrologic groups. For update features, we will use the land cover to fill the gaps. Let's save this into the MID data. Here on folders, flood risk using GIS and multi-criteria. Let's call this SAG SimDiff and click OK. Oh, I missed the folder. Let me just repeat the process. Here, click OK. And set the environments. As you can see, what we did here was fill the blank spaces using the land cover data. But what we actually want is not the land cover itself. We want to assign a soil hydrologic group from B to D. So what we are going to do is assign to each land cover element the nearest soil hydrologic group using the near tool in the geoprocessing tool. So let's search for near, click on this one, choose the sim difference, the symmetrical difference as the input features, and near features we will use the soil hydrologic groups. After that, we only need to set the environments, in this case the extent as the DM, and what this tool will do is to create new fields in the attribute table of the symmetrical difference layer. These fields will include information such as the near feed, near distance, along with the attributes, in our case the hydrologic soil group, from the nearest polygon. We can actually open the attribute table of the symmetrical difference, so we see the result appearing in real time. So let me just click run. And we see that the table was updated, and if we move the scroll bar to the right, we can see that we have the near feed and also the near distance. So what we need to do now is to join this table using the soil hydrologic groups table and having as a common field the near feed from the symmetrical difference layer and the feed from the soil hydrologic groups layer, we can then perform a join operation. This will allow us to transfer the soil group information B to D from the nearest valid soil polygon to the land cover areas that we are missing data, so effectively filling the gaps with the closest valid classification. So let's use these elements in the join operation, feed here on the soil hydrologic groups. We can now click OK to perform this operation. And now, as you can see, we have the soil hydrologic groups in this symmetrical difference layer. Okay. Since we cannot proceed to any geoprocessing operation in a joined table, we need to export this joined table into a new feature. So let's right click and export data. Let's save this into the metadata folder. We can call this maybe something like SAG simdiff underscore join. Let's click OK. OK once again. The result of this layer is visually identical to the previous one, but as we can see, the attribute table is no longer based on a join. It has become a single standalone table. We can remove this one. If we open the attribute table, we can see that each row now has the value of the nearest soil hydrologic group. If we change, for example, the symbology and choose the field SAG_1, we can visually confirm a spatial relationship with the original soil hydrologic group's shapefile. Of course, the level of detail isn't perfect, but this is one of the valid approaches to help fill in the gaps and correct the error in the dataset, especially when you need a complete and continuous layer for further analysis. Next, what we need to do is combine the two elements, and for that we are going to use the merge tool. So just search for merge, this first one, select the soil hydrologic groups and the SAG simdiff join, set an output folder, this will be metadata as well, SAG merge, and set environments. After that, we click on the run button, and there we have our result. Let me remove this one. With the merge, we can see that there are still blank areas, and I believe this is just a symbology issue, since after performing the merge, data got split across the columns. So let's check this. Let's open the attribute table of the SAG merge, and we can see the SAG, and if we sort ascending, we can see that there are no values here. So we just need to transfer the values from one column that appears further to the right to this one, or from this column to the other using the field calculator. So we see that here we have the values, and right there at the left we didn't. So, and if we sort ascending, we don't have here but have on the other column. So we just need to use the field calculator and place these values on the other column. To do that, I will just select all the rows that don't have values in the SAG field. So I just select the first one, click Shift, and select the last one that don't have any values. Let me just see this one. Next, we right click on the SAG field. Here, click on Field Calculator or Calculate Field. And we just need to say that we want this this selected column needs to have the values of SAG1. Okay, so because this here we have the values. So we just right click on SAG_1 and click apply or OK to fill the data. There we go. This way, we now have a fully populated SAG shapefile. We can even confirm this by double-clicking the SAG field to sort the values. If there were any blank entries, they would appear at the top or bottom, but since none are showing up, we can be confident that all records are now complete. Let me just change the symbology again. Let me refresh, clicking on add all values. And there we go, we have all the values with the same color. This is now resolved, and now we are going to start assigning the curve number. To do that, we need to combine the land use and the soil type. We'll begin by searching for the Insert Intersect tool, which allows us to overlay these two layers and generate a new one that contains the combined attributes of both. This will be essential for assigning the correct CN values based on their intersection. So in the geoprocessing tool, just search for intersect. The input features will be the SAG merge and the land cover. And here the SAG merge. The output feature class. We can call it CN_classification, for example. Click OK and set the environments and click run. Here we have the result. Let me just remove a few elements because the project is getting quite heavy. So let me just remove this one. And here on CN classification, let's open the attribute table to see the intersection of these two elements. As we can see, we have the land cover information here, and further to the right we have the corresponding soil hydrologic group values here. The first thing we need to do to calculate the curve number is to create a new field in this shapefile where we will insert the CN values. Click on Add Field. I will call it CN. The type will be double and click Save. As I mentioned earlier, we need to match the original reference tables with the land use categories available in our dataset. In my case, I've already done that work in this Excel file. This Excel file will also be shared along with all the other data used in this project. As we already saw on the website, this is the structure of these tables, and if I go to the last sheet of this Excel file, we can see a direct correspondence with the data we are using. For example, for the areas classified as artificialized, I use the average curve number values from the category developed urban areas. For example, we can see that for cork, home and home oak, eucalyptus and maritime pine, I use the woods type. For the other broadleaf trees, woods as well. Shrubland, I use the brush. So I try to assign the values that best match my data. I'm going to place the Excel file side by side with ArcGIS Pro, and we will start filling in the field we created earlier with the appropriate curve number values. To do that, in Map, we go to Selection and click Select by Attributes, Add Clause, and let's start with land cover is equal to artificialized, add clause again, then we say hands, and now we need to select the SAG file. So here select the SAG_1. Actually, it's not this one, but the SAG only because the SAG1 doesn't have all the values. So it's this one. And we can start with the B and click apply. What this does is select only the records where this expression is true, in this case artificialized land with SAG value B. It gave an error because I had add to the current selection, set as the selection type, but I need to change it to new selection. So let's change it here. And let's click apply now, and now it should work. Actually, let me just remove this. And let's click apply, and now it should work. I'm going to click this button here to display only the selected features. And as you can see, only the elements with land type artificialized and SAGB are currently selected. To enter the value, right-click on the name of the column at the top, and then select Calculate Field. And as we can see here in the Excel file, the value of artificialized with SAG type B, it's 81. So here on Calculate Field, CN needs to be equal to 81. And click apply. Now we do the same for the C type. So change this to C. Click apply. The C type is 87. So change the CN value from 81 to 87 and click apply. And finally, the last one, it's the D. And this one has the value of 89. Click apply. We now have all the artificialized areas filled in, and we need to repeat this process for all the other entries in our table. Since this is a very repetitive task, I'm going to move on to the next phase of the workflow. Now that we have all the values in the table, I'm just going to represent them on the map by changing the symbology. So here we have all the CN values. Let me just close the table and change the symbology of this shapefile. Right click on the shapefile and click on symbology. Let me change the field type from land cover to the last one, the CN. Here on color scheme, I will select format color scheme, and right at the back, I will just select, I think it's continuous color scheme. This one will be pink and this one will be blue. And let's click OK. So the lower values will have the pink color and the higher values will have a more bluish color. Obviously, this type of analysis must always be done in a raster format, so we now need to convert this shapefile into a raster file. So in the geoprocessing, just search for polygon to raster. Click on this first one, drag and drop the CN classification into the input features. The value field will be the CN. Let's select the output. This will be saved in the mid data as well. Here. And we can call it, for example, CN underscore raster. Here, let's click OK. Here we don't need to change, priority field will be none, and here we need to select the cell size In this example, this will be 25. Since we are using the DEM as both the mask and snap raster, and the pixel size of that DEM is 25 meters, I'm going to enter 25 in this field to match the resolution. We set the environments and click Run. There we go. Let me just remove the shapefile. So let me just remove this file here. And there we go, we have the CN raster here. So now if we go to the article once again, we now need to reclassify these values from 1 to 5. Okay. So as we can see here, the bigger CN values will have a value of 5 and the lower will have a value of 1. In the example from the article, the range of values was narrower, going from 74 to 94, while in our case the values range from 58 to 100. However, by personal choice and to stay consistent with the original methodology, I will also use the same scale. So values below 74 will be assigned a class of 1, and values above 94 will have a value of 5. So going back to ArcGIS Pro, I will just search for the tool Reclassify once again. I will just drag and drop the CN raster as an input feature. So the first value will be below 74 and will be assigned a class of 1. So here let me just change this value to 1 to every number that is below 74. 74 will have the value of 1 as well. Now from 74 to 79 will be assigned, it will be assigned a value of 2. So these three numbers will have a value of 2. For the class number 3, it's 86, so from 79 to 86 will have the value of 3. Then from 86 to 90, in this case 91, this will have a value of 4. So the value 87, 88, 89, 90 and 91 will have the value of 4, and 94 and 100 will be 5. This will be, yes, this will be one of the final results. So this result will be saved in the results folder, and this will be called R_CN. Let's click on OK and set the environments and click Run. So here we have our result. To keep things consistent, I'm also going to change the symbology for this layer as well. So the class number 5 will have a red color. Number 4, it's orange. Yellow for number 3. And 2 and 1 will have green colors. Let me just remove this raster and drag the final CN result to the bottom of the distance to streams raster. Let me just also give this the number 4 to know that this is the element number 4. Let me drag this to the bottom. Thank you for watching. If you like this type of content, don't forget to like, subscribe and comment what you want to learn next.